In the fall of 1907, the first crews disappeared underground into a mountain north of Los Angeles. Nobody else had started yet. The tunnels had to come first, because the tunnel that would control the entire project's schedule was 5 miles of solid granite, and Mulholland knew it would take years. Everything else, the mule teams, the concrete crews, the desert camps, spread out across the route the following year. By 1913, they had built a 233-mile artificial river across some of the harshest country in the American West, without a single pump. At the time, it was one of the largest engineering projects in the country. The man leading it had no engineering degree. What gets me is not just that they built it, it is how. How do you move a river across desert and mountain without a single pump? Let me take you through how the Los Angeles Aqueduct was actually built, mile by mile, tunnel by tunnel, and siphon by siphon, and how I used historical records, maps, engineering reports, and AI tools to help reconstruct the project along the way. But first, you need to understand why Los Angeles became desperate enough to try. Los Angeles at the turn of the century was a city betting on growth it could not water. The population had pushed past 100,000 and kept climbing, but the whole place ran on a single source, the Los Angeles River, which in a dry year was barely a creek. A long drought from the 1890s into 1904 made the problem impossible to ignore. William Mulholland, the superintendent of the city's water department, had spent years measuring exactly how fast demand was outrunning supply, and the numbers were not survivable. The answer came from Fred Eaton, a former mayor who knew the Owens Valley, more than 200 miles to the north. The Owens River ran down off the Sierra snowpack, carrying far more water than the valley's farmers were using. Eaton's idea was blunt. Move it. Build a channel long enough to carry that water to Los Angeles and let the slope of the land do the work. Getting the water rights was the ugly part of the story. Eaton quietly bought up land and river rights in the Owens Valley, while many locals believed he was working for a federal irrigation project. By the time the valley understood what was happening, Los Angeles controlled the river. The city eventually held around 130,000 acres and roughly 85% of the valley's private land. President Theodore Roosevelt backed the plan as exactly the kind of public works his administration wanted. That fight is its own video. What I want to show you is what came next, because once the rights were locked up, the city still had to build the longest aqueduct on Earth, across desert, fault lines, and solid mountain rock. The route ran 233 miles. It started at an intake on the Owens River at about 3,800 feet of elevation and ended at the northern edge of the San Fernando Valley, around 1,460 feet. That drop is the entire reason the thing works. Mulholland designed the channel to fall at an average of roughly 2 feet per mile, just enough tilt to keep the water moving without tearing the lining apart. Steeper, and the flow would scour the channel. Flatter, and the water would stall. He had to hold that grade across the whole length. The water never ran in one kind of channel. It started where crews diverted the Owens River into an unlined canal a few miles north of Black Rock in Inyo County. Through the soft ground of the upper valley, electric-powered dredges cut the open ditch. Across flat, exposed stretches farther south, crews built covered concrete conduit to cut evaporation and keep the water clean. Through mountains, they bored tunnels. Across canyons too deep to bridge or fill, they sent the water through steel siphons that dropped it down one wall under pressure and pushed it up the other. The system wasn't one thing. Roughly 40 miles of tunnel through mountains, nearly 100 miles of covered conduit, open canals across the valley floor, and steel siphons dropped into canyons where nothing else would work. To manage a job spread across that much ground, the aqueduct was divided into multiple construction sections, each responsible for its own stretch of the route and operating almost like a separate project. Paying for it took 2 votes. In 1905, voters approved a $1.5 million bond to buy the land and run the surveys. In 1907, with the route mapped, they approved a far larger $23 million bond to actually build it. Mulholland told the city he could finish in about 5 years for that money, was named chief engineer of the project, and put his own estimate on the line. Here's the part that still gets me. Mulholland had no formal training. He had taught himself hydraulics and mathematics out of borrowed books while working his way up from ditch tender. And the city handed him the largest, most expensive municipal project in American history and told him to go build it. You cannot build a 233-mile structure across empty desert until you can get men, food, cement, and steel to every point along it. So before any water channel went in, the city built the infrastructure to build the aqueduct. The Southern Pacific Railroad laid a new branch line, about 118 miles of track running north from the Mojave Rail Hub toward Olancha, so freight could reach the central stretch of the route. The line existed to move an estimated 14 million ton-miles of material, and nothing else out there could carry that load. Crews graded roughly 500 miles of roads and trails and strung around 240 miles of telephone line, so the scattered work sites could talk to each other and to Mulholland. They put up more than 2,300 buildings and tent camps. By the end, the project had moved something like 320,000 tons of material into the field. Keeping thousands of men fed and watered in open desert was an operation by itself. Water for the construction work, and for the men, often had to be hauled or piped into camps that sat miles from any natural source. And then they hit the problem that nearly every megaproject hits: concrete. An absurd amount of it. The aqueduct needed enormous quantities of it, and hauling finished cement from distant mills would have been ruinous. So the city built its own cement plant in the Tehachapi Mountains, sitting on a huge limestone deposit. Mulholland named the spot Monolith. The plant turned out around 1,200 barrels of Portland cement a day and fed the concrete work for the entire line. The mix used a volcanic ash called tufa, processed nearby, which made a stronger cement than ordinary Portland alone. To feed the plant, the city ran its own limestone and tufa quarries and built regrinding mills out at the tufa pits. Power was the last piece. The tunneling machinery and the camps needed electricity, and there was no grid out there. So the project built 2 hydroelectric plants of its own on Owens Valley streams, the Cottonwood and Division Creek plants, to run the drills, the lights, and the work. None of that is the aqueduct. All of it had to exist before the aqueduct could. The city essentially built a temporary industrial economy strung out across 200 miles of wilderness, and only then started on the thing the economy was there to build. The hardest, slowest part of the whole job was underground. The route had to pass through mountain after mountain, and there was no way over them that gravity would tolerate, so the crews went through. 142 separate tunnels had to be driven along the line. Depending on how temporary works and excavation sections are counted, sources place the total tunnel excavation at roughly 43 to 52 miles of bore through rock. The worst of them was the Elizabeth Tunnel under the crest of the San Fernando Mountains, about 45 miles north of Los Angeles. It ran just over 5 miles, 26,870 feet, straight through solid granite. Crews started it by hand in the fall of 1907, digging in from both ends, the north portal and the south portal, aiming to meet somewhere inside the mountain. The granite was hard enough, but parts of the tunnel passed through loose, wet ground that constantly tried to collapse. So the crews had to carry it on continuous timber supports as they advanced, and then line the finished tunnel in concrete. The Board of Engineers had figured this tunnel alone might take 5 years. And since no Owens water could reach the city until Elizabeth was holed through, the entire timetable hung on it. Mulholland threw the best equipment and the best men at it. The crews switched to compressed air machine drills instead of hand steel, and the city paid wages high enough to pull experienced hard rock miners off other jobs around the West. The cycle was the same every shift. Drill a ring of holes into the rock face, pack them with dynamite, blast, haul out the broken rock, advance, and start again. Then he set the 2 crews against each other. He put them on a bonus system, paid by the foot, and they started racing. In 1 month, the miners drove 604 feet of tunnel through granite, which stood as the American record for hard rock tunneling at the time. The two headings met under the mountain in late February 1911, almost dead on line. When it opened, Elizabeth was one of the longest tunnels in the United States. This is the part I keep coming back to. The men underground had no GPS, no lasers, no satellites. Two crews started drilling toward each other from opposite sides of a mountain, more than 2 miles of solid rock between them, working off survey lines drawn up on the surface, and they met in the dark within inches of where they were supposed to. That is not luck. That is arithmetic done correctly by people who could not afford to get it wrong. Across the project, the tunnel crews set a brutal early pace. In the first 11 months of work alone, they drove 22 miles of tunnel. Where the line hit a canyon too deep to tunnel under or fill across, the water went through a siphon, a giant sealed steel pipe that ran down one side and back up the other. The water's own weight built the pressure going down and carried it up the far wall. The most famous was the Jawbone Siphon, crossing Jawbone Canyon in the Mojave. It ran about 8,095 feet of steel pipe, between 7.5 and 10 feet across, and dropped the water 1,000 feet to the canyon floor before climbing the other side. The thickest steel plate in it was more than an inch thick, and the whole siphon weighed over 3,200 tons. The longest siphon on the project crossed Antelope Valley at 21,800 feet. There were 13 of these inverted siphons in all, most of them riveted up from steel plate and set on concrete piers above the ground rather than buried. Getting steel pipe that size into a desert canyon with no road was its own feat. The pipe came in sections weighing as much as 26 tons each. Out where the railroad could not reach, the only thing that could move them was mules, and ordinary teams were not enough. The haulers hitched up teams of 52 mules to drag a single pipe section across the sand. Think about that for a second. The most advanced public works project in the country, the one setting world records underground. And the way the pipe reached the canyon was a line of 52 mules leaning into a harness. The men who built all this lived rough. The workforce was largely itinerant labor, drifters the era called bindle stiffs for the bedrolls they carried on their backs. The payroll swung wildly with money and weather. It peaked at 6,060 men in May 1909, then crashed to around 1,150 in 1910 when funding got tight, before climbing back to between 2,800 and 3,800 men through 1911 and 1912. Many thousands of men passed through the camps across the 5 years. They were a hard mix of immigrants, Greeks and Serbs and Bulgarians and Mexicans among them, working in Mojave heat and mountain cold. The camps were crude, sanitation was thin, and disease moved through them. At least 43 workers are known to have died building the aqueduct, and the real number was almost certainly higher. By 1912, the work hit a problem nobody had planned for. War broke out in the Balkans, and so many of the project's southeastern European workers left to go home and fight that it caused a labor shortage on the line. The aqueduct was finished in the fall of 1913, on schedule and under its budget. On November 5, 1913, the city held the opening at the Cascades, the stepped concrete spillway at the north end of the San Fernando Valley, where the water would tumble down into the basin. A crowd estimated between 30,000 and 40,000 people came out to watch. Many had driven out from the city for the day. When the gates opened and the water came roaring down the concrete steps, the crowd surged toward it, and people scrambled down to fill cups and hats from the first Owens River water to reach Los Angeles. The water came down the cascade. William Mulholland stood next to Mayor Henry Rose, who was supposed to formally accept the aqueduct on behalf of the city. Mulholland, never much for speeches, and unable to be heard over the crowd and the band anyway, gave up on his prepared remarks. He turned to the mayor, pointed at the water, and said the 5 words that became the most famous line in the city's history. "There it is. Take it." That was the whole speech. 5 years of tunnels, siphons, mule teams, and concrete, 233 miles of it. And the man who built it summed up the moment in 5 words and sat back down. The next morning's Los Angeles Times ran the headline that the mountain river was now flowing to Los Angeles. It had been built in 5 years, on time and under the money the voters had approved, which for a job that size was almost unheard of then, and is rarer now. At the time it opened, only the Panama Canal outranked it as an American engineering project. The aqueduct delivered a steady flow of about 485 cubic feet of water per second, several times what the Los Angeles River had ever given the city, and enough on paper to carry a population of 2 million. What that water did to Los Angeles is hard to overstate. The city had been a few 100,000 people pinned to a small river. Within about a decade of the aqueduct opening, the population passed 1 million. The San Fernando Valley, dry ranch land before, filled first with orchards and then with houses, all of it drinking Owens Valley water. The modern city is, in a real sense, something the aqueduct made possible. The Owens Valley paid for it. The river that had fed its farms now ran south, and over the following years Owens Lake dried up into a salt flat. The valley's farmers fought back, dynamiting the aqueduct more than once in the 1920s in what came to be called the California Water Wars. The water never came back. So it is two things at once. It is one of the great engineering achievements of its age, built ahead of schedule by a self-taught man and an army of drifters and mules, and it is the reason an entire valley to the north went dry. Both of those are true, and you cannot really tell one without the other. If this caught your attention, hit subscribe and give the video a like. And let me know in the comments, what city, era, or place do you want me to cover next? See you in the next video.